Okay, good morning everybody. We continue our lecture about quantum fluids. I'm just reminding you what we have done in the last lecture. So we had a model with three energies. This was our energetic spectrum. And we had E1, E2, and E3. Okay. And we looked on a fermionic system with occupancy, double occupancy per each level. So we had an occupancy of particle for an energetic level. It can have occupancy with spin up and occupancy of spin down. So no more than two particles with different spins per level. Essentially, we represented everything in the terms of the Fermi function. More specifically, per particle, the occupation of a level with a specific spin was F I. So the probability of a specific level I to be occupied was 1 over 1 plus e to the power beta epsilon I minus beta. Okay, so this is what we have done, and afterwards we plotted this Fermi function. So F is a Fermi function, and mu was the Fermi energy. Why Fermi energy? Well, basically, the Fermi function in the limit where epsilon, the energy, divided by mu is in the limit of very small temperatures. In the limit of very small temperatures, all the levels up to mu are filled, and all the levels that have energies with energies larger than mu or larger than the Fermi energy are completely empty. So we have this block. This is F, and this was epsilon divided by mu. Here was 1, and here was 1/2. And the different energies or different behaviors were such that, well, first of all, they all cross this point of 1/2 and a half. And what we had is different behaviors as a function of what is mu. So we have taken mu as a function of the temperature, and we plotted the behavior for different mu. So this was when mu was equals K Boltzmann T. We can increase the value of mu, right? And then we went to something that looks like this. This was mu equals 4K Boltzmann T. Then we went, this is 1. Then we went to mu equals 10 K Boltzmann T. And in the limit, when mu is much larger than K Boltzmann T, what we can mean by that, we can say, well, mu is a constant, and we decreased our energy. Our temperature. So in the limit, when the temperature is very low, and then mu in terms of K Boltzmann T is very high. We obtain almost a delta function for the behavior of the Fermi function. Okay. This is t goes to 0. T goes to 0, and mu is constant, so mu is much larger than k Boltzmann t. Let's say this as mu is much larger than k Boltzmann t. Mu is the Fermi energy. Fermi energy. Sometimes it's noted as E Fermi, EF. What we mean by this, that we decrease the temperature, increase the temperature, or this plot, you can think of, well, I'm actually somehow changing mu and I keep the temperature constant, which is okay. But usually what we mean by this, well, mu is a constant and we're changing RT. Okay? Because if mu is something, usually when we developed, not usually, when we developed the grand canonical potential, mu was assumed as constant for the reservoir. And the temperature was also assumed constant, and we can play with each of those values, either the temperature or the chemical potential. Now, what we learn from this graph, specifically what we learn is that for the very low temperatures, mu is something, so we have a very distinctive Fermi energy, or a Fermi level, that at the low temperatures, the system is going to occupy all the levels up to this energy, E Fermi, okay? And none of the states that have energies above E Fermi is going to be occupied. This is this step function. 1 for anywhere inside this range where 1 is epsilon equals to 0, epsilon equals to mu, and 0 for any other energies. Think of it, what actually happens. In the low temperatures, the system, or all the particles, are trying to access the lowest energies. Okay? Now, they cannot all sit together at the most lowest energy. Why? Because it's a fermionic system and there are always some sort of interactions because of this Pauli exclusion principle. So what actually happens is that they pile up in all the possible energy levels up to the most, as the maximal energy level, which is we call E Fermi, and that's it. That is what happened at t goes to 0. When t is not exactly 0, this is then not exactly, this is just not exactly a step function, and it have some sort of a width. Great. We'll come to this point in a few minutes about the width. I just want to remind you that we had a specific example, and in this example we wanted to compute mu, mu as a function of a temperature and the average number of the particles. So remember, the average number of the particles is defined for the system, is defined by mu, because an average equals to what? Equals to 2 divided by epsilon beta, epsilon 1 minus mu, plus 1, plus 2 divided by e to the beta, epsilon 2 minus mu, plus 1, plus 2 divided by epsilon beta, epsilon 3 minus mu, plus 1. How we got this formula? So it was very easy. An average was a sum of 1 multiplied by 1 divided 1 plus e to the power of beta epsilon I minus mu. Okay, I goes from 1 to 3, plus 0 multiplied by 1 minus 1 divided by 1 plus e to the power of beta epsilon I minus mu. Okay. So this is the probability that the level is occupied, and if it's occupied only by one particle. Okay. And this is the probability that the level is not occupied. If it's not occupied, how many particles we have there? 0. Okay. Now each of those should be multiplied by 2. Why? Because we have a degeneracy of 2, spin up or spin down. So there is 1 multiplied by 2, and this guy is multiplied by 2. And we see this part we completely don't care about because it's 0 multiplied by something. So we left only with this, which is exactly what we have written before. Now, as we see, n average is determined is some function, let's call it g, of what? Of beta and mu. Okay, beta and mu. And of course the different energies, but the different energies of the system we cannot control. They are frozen. Okay, this is a given system. We can control the chemical potential because it's in a bath, and we can control the temperature. Right? Now, what we want to actually do is not to write n as a function of beta and mu, we want to write mu as a function of beta and n. And we claim that it's always possible to do so. Why it is much more convenient to do this? From the experimental perspective. So if I'm looking on a system, well, here I have a system of 3 levels. So it's a little bit of a hypothetical system. But if I'm looking on a fermionic system, like for example, electrons in a metal. Okay. Now, for this system, I don't really know how to control the chemical potential. But I do know how to control, or more exactly, I know what is the average number of the electrons in the metal. I can control this. I can use a specific metals, and I can actually control that the number of electrons won't escape the metal at all. So basically, I have much more control over n than over mu, average n. Okay. This is A. B, sometimes what I actually want to learn is not, well, the average number of particles. This is I can approximate by knowing what is the density of the carriers inside the metal. But I actually want to calculate what is the E Fermi in the system. Why? Because it's a property, the property of the whole system at low temperatures. I know, if I know what is the E Fermi of the system, I know up to which point all the different energies are going to be filled up. Moreover, I can approximate what are the states or what are the energies that are actually participating in the conduction process. Because in the conduction process are going to be participating only particles or only states that are partially filled and partially unoccupied. A level which is completely filled, okay, all this region over here, which is always filled, is not going to participate in anything. They're just sitting there. And only the electrons and only the energetic levels that are partially, that can be occupied and unoccupied, you basically have those fluctuations, right, that can accept energy and contribute energy. Right? Only those states are going to be important, as you would see in the class on solid state. So the E Fermi, what is E Fermi, is very, very important. Specifically for the system of 3 levels, and we had our example of 4 particles. Okay? We had the example of average n equals 4. What we have, and epsilon 1 equals epsilon 2, what we have shown is that mu in the limit of the t goes to 0, mu was exactly epsilon 1 plus epsilon 3 divided by 2 plus 1/2 k Boson t log 2. 1/2 K Boltzmann T log of 2. Okay. This is what we have seen already. I'm just reminding you the whole procedure. So for the system at the lowest temperature and the specific degeneracy, I would plot it over here. So if I'm having my energetic spectrum, this is my energies, and I have epsilon 1 and epsilon 3. What is the degeneracy of epsilon 1? The degeneracy of epsilon 1 is 4. The degeneracy of epsilon 3 is 2. Why 4? Well, basically there are two energetic levels, epsilon 1 and epsilon 2, and each of those levels have two possible spins, right? It can be occupied with a spin up and spin down. Alright, and what we see is that exactly at the temperature, when temperature goes to 0, the Fermi level, the Fermi energy, sits exactly between those two, epsilon and epsilon 3. Which basically states, well, all the states, or with energy equals epsilon 1 are going to be filled, and no particles are going to occupy the energetic level epsilon 3. What will happen if we increase our temperature a little bit? So we see that we have this contribution of 1/2 K Boltzmann T. So this Fermi level will be shifted upwards as temperature will grow. And this is basically a pretty general feature of the Fermi energy. It is always shifting away from the more degenerate levels. So if we have two levels, one is much more degenerate than the other, and the energy in the Fermi level, Fermi energy sitting between them, as a function of temperature, the Fermi energy will try to escape away or to move away from the situation where the more I'm sorry, when there are where the degeneracy is higher. Okay, this is something pretty general about Fermi energy. It's always trying to escape to the situations where the degeneracy is lower. Okay, so what we understood from this example, or I tried to make you feel a little bit, is that everything in a fermionic system, at least at this very simple fermionic system, can be described by F, Fermi function. It actually gives us the distribution of occupied and occupied, if the state is occupied and occupied. And eventually, this property of mu, which we called Fermi energy, it gives us the low temperature behavior, and actually what are the states that are occupied at very low temperatures. And moreover, it also produces us the states that are contributing to the gain. So the particles, what is going to happen in this system? So if you leave it alone, there are some fluctuations in energy of the system and the fluctuations in the occupations of the system per specific level. So some of the levels are going to be occupied, unoccupied, occupied, unoccupied. What it means? It means that the Fermi function for those states is going to be different from 0 or 1. And those only the states that will feel some sort of fluctuations. So for example, if you have a process, the particles are changing their states, only the states when the F is smaller than 1 and greater than 0, only those states will have those fluctuations. All the other states, either they are unoccupied, so there is nothing going on there, or they are fully occupied all the time, and it's also nothing going there. Okay. So only the states that participate in some sort of a physical process during the time that we're looking on the system are only the states where F is between 1 and 0. Right? Significantly larger than 0 and significantly smaller than 1. So if you look on F, as a function of epsilon divided by mu, and again, we have this 1 over here and 1/2 over there, and F goes, something like this. What I'm saying is the energetic levels that are contributing, that have some sort of fluctuations in them, significant fluctuations, are this band around energy equals to mu Fermi, to epsilon Fermi. Okay? So only the states that are basically in this region are participating in the process of changing the number of particles, changing their energy. All the other states either fully occupied, so nothing happens there, there are no fluctuations, or fully unoccupied, so there is nothing also going there, no particles ever reach those states. Okay. Now, if you look on this function, what is f? F is equals to 1 divided by 1 plus e to the power of beta mu epsilon divided by mu minus 1. Okay. We see, so either this function decreases towards 0, or if we flip everything upside down, we see, well, also here the function is decreasing towards 1. So what is this average size? Actually, this region over here around epsilon equals epsilon Fermi is always what? K Boltzmann T. So this part is K Boltzmann T, and this part is also K Boltzmann T. Okay. How do we see this? Well, basically, if we have F equals 1 divided by 1 plus e to the beta e minus mu, okay, what we need to approximate is how fast either this guy grows or how fast this guy decreases to 0. So e to the minus mu is either greater than 0 or it's smaller than 0. Okay. In both cases, beta, or I might say 1 over beta, is the speed. This is the exponential prefactor of the increase or the decrease of the function, and in each case it's 1 over beta, so it's equals to K Boltzmann T. Okay. So we have a total width, energetic width of 2K Boltzmann T. This is the width of 2K Boltzmann T. Okay. Where something actually happens. In this region, the Fermi energy is lower than 1 and significantly higher than 0. Everything else here, because of the exponential decrease of the function, when we take energetic levels that are 2K Boltzmann T and 3K Boltzmann T higher than the Fermi level, they are going to be completely unoccupied. If we take energetic levels that are 2K Boltzmann T, 3K Boltzmann T away from the Fermi level, they are going to be occupied all the time. So again, nothing happens there. And only in this region, the level is partially occupied. F Fermi is between 0 and 1. It means, if we look on this level, sometimes it's going to be occupied, sometimes it's going to be unoccupied. And this is the process we are looking for, because this change, the rate of change of the specific level, this is what determines a lot of physical processes. Okay, so very good. Now we can continue to a little bit more complicated question, and it is, what happens in a real metal? Okay, so up to now, I was telling you stories about very simple three-level system. Okay, it's fermions. There we're occupying only E1, E2, and E3. Okay. And everything was very, very simple. What happens in the real matter? So electrons. Here the particles were not interacting. Although they were fermions and they were interacting due to the statistics, okay, but there were no effect other than the statistical effect of one particle on the other. It was only the Fermi exclusion principle. Now, what happens in the metal? We have electrons, and electrons repel each other according to the Coulomb law, right? Coulomb law goes as 1 over distance squared. So basically the particles feel each other all the time. It doesn't really matter how far away then from each other, they always will feel. So if I would take one electron here, the other electron over there, this is the distance between them, R, the force between the two particles going as 1 over R squared. And it's always there. So it's not, you cannot say, well, it's decreasing exponentially, so if an exponential decrease to 0 fast enough, etc., 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 it's going to disappear. No, this force is never going to disappear, and probably you should take it into account always. So what it seems to me, to us, I'm sorry, is that in order to describe electrons in a metal, what we should do, we should take somehow into account this interaction. And well, actually up to now we haven't done anything with interactions. Everything we have done eventually is free particles. They have different densities of energies, etc., etc., but they've always been free. This is what we made. This is because of this fact we actually managed to solve everything. So it's going to be hard. The answer is, and how we are going to solve it if it's hard? The answer is, well, actually we're not going to solve this problem. Nobody really knows how to solve this problem for a large number of particles. So what do people solve when we try to describe electrons in a metal from the statistical mechanics point of view? They solve free particles. They solve gaseous particles. They are electrons, but we say they do not interact with anyone else, and it's called a Fermi fluid. Okay, what is a Fermi fluid? Fermi fluid is particles or electrons that sit inside the metal, and they completely do not care about each other. They only care about, well, not to occupy exactly the same state because there are Pauli exclusion. So Fermi fluid it's a gas of free fermions. Why are we going to study, or basically to look on the system with it's a gas, and say something that, well, what we're actually doing here are electrons inside a metal? Doesn't make any sense. Well, it actually very much does, because what I have told you here about the interactions of two electrons is completely true. It is true, but only in the case when there are just only two electrons, or three electrons, or four electrons. Basically, there are only electrons in the system. But what happens in the metal? So actually, those electrons, they came from somewhere. So there are molecules with missing electrons. They are ions, right? With positively charged now, okay? Because if there are no spare, there are missing electrons. The remaining molecule is going to have more protons than electrons, and it is going to be positively charged. And they also have some sort of a field and Coulombic interactions. Eventually, those are screening fields. And in those screening fields, what they actually do is that they kill the Coulomb force or the Coulomb interactions between different electrons in some sense. What actually happens is that you have a Coulomb interaction, but you have also the medium field acting on the electron. And this medium field is basically changing the 1 over r squared interaction between the electron into some exponential interaction. So there is some specific interaction range between different electrons. Okay? They sometimes feel each other, but if the distance or the average distance between the different electrons is not small enough, basically the electrons are not going to feel each other, or almost do not feel each other. Moreover, we would see that the quantum statistics actually causes the effective energy of the system, or the effective energy of the system due to the quantum statistics is much more higher. It's extremely high if it's compared to the interaction energy. Their temperature of these free particles is extremely high, and basically we're saying, well, we don't really care about this interaction. There is some sort of interaction. It's not infinite. It's not going to infinity, the interaction range. It's small. B, the quantum statistics eventually overcomes this issue. For most cases. Sometimes it is not. Sometimes you have a very specific situation when the interaction of the media and the particles is actually causing those guys to change their nature, and instead of fermions to become to bosons. But maybe you'll hear about this later. So what we are going to do, we're going to treat those particles. We're going to treat those particles as fermions. Each particle, okay, also what are then the accessible states? The accessible states, epsilon km, are p squared divided ks, p squared divided by 2m, so there is only kinetic energy. Okay. This means that is h bar k squared divided by 2m. M is the mass of the electron, h bar is h bar, Planck constant divided by 2 pi, and k is the wave vector. Okay. So when I want to describe different states of the system, I want to describe what are the different k's that I will have there. Exactly as we had in the Debye model, exactly as we have for the radiation model, is the same at math. Okay? So how many states? I can go to the density of states. Alright. Now, as we already seen for the system of 3 states, exactly the same works for the system of huge number of states. If you want to write the partition function, the partition function is factorizes. Okay? Why is factorizes? It factorizes because we are using a grand canonical potential, grand canonical ensemble. Okay? So what we can do is to describe the partition function as a multiplication over all different k's and all different s's. S can be 1/2 and minus 1/2, so this is the spin. And you see if there are no magnetic field, it does not affect the energy. And what is going to be here? This is z, k, and s. What is zk of s? Zk of s is a partition function for a specific level, right? How we can obtain this formula? Well, we need to write the partition function, use the occupation of each level, so how many particles can be per level 1 and per level 2, and there are only 1 particle or 0 particles, and perform exactly the same summation as we have done already for the 3-state states model. It's exactly the same math. You just write this long partition function, and then you see, well, I can actually separate it into different states, because the total energy of the system is always described by how many particles are sitting in each state, and you sum up over all the different states. Why? Because the particles are not interacting. You don't care about the interaction between them. The energy of the system is only the occupation number, or the sum of the occupation numbers of all different systems. Sorry. To make a long story short, Z was a sum over nk, or n1, n2, n3, etc. And here I had e to the power minus beta n1 epsilon k1 plus n2 epsilon k2 plus n3 epsilon k3 plus etc. minus mu n1 plus n2 plus n3 plus n4, etc., etc., etc. So those are the basic contributions of the partition function for the grand canonical ensemble. And what we have done, okay, exactly on the same model, we just said it's a sum of n1 multiplied by e to the power minus beta n1 epsilon k1 minus mu n1 multiplied by a sum of n2 multiplied by e to the beta n2 epsilon k2 minus mu multiplied by n2, etc., etc., etc. Now each of those guys is behaving very simple, because n1 goes from 0 to 1. So we can describe this, nk goes from 0 to 1, e to the power beta n k epsilon k minus mu nk. Okay, it simply equals to 1 plus 1 because it's e to the minus beta 0 multiplied by epsilon theta minus mu multiplied by 0 plus e to the minus beta epsilon k minus mu. And this is simply zks. It does not depend on s, and it is 1 plus e to the minus beta. Instead of epsilon k, what we have here, we have h bar squared k squared divided by 2m minus mu. Okay. This is this z. And we have a multiplication of a lot of them for all different cases. Now I can ask myself a question, well, if I'm taking a very specific k and s, what is the occupation probability of this level? What is the probability that I will have a single electron or a single particle that will have a spin s and energy of h bar k squared divided by 2m? So psi k and m equals e to the power minus beta of epsilon h bar k h bar squared k squared divided by 2m minus mu divided by 1, we should write it as z k and s equals psi k and m equals 1 divided by 1 plus e to the power beta of h bar squared k squared divided by 2m minus mu. This is occupation probability of state k and m. And we see that this is simply a Fermi function. Exactly as we had before. So everything we have learned and everything we had said about the three-state model stays exactly the same for the Fermi fluid or the gaseous description of electrons and matter. Okay, so if we have the partition function, the next step is to calculate the grand canonical potential. What is the grand canonical potential? Is minus k Boltzmann T log of z. This is how it's defined. This is the state function. The moment we calculate the state function, we know everything else. So psi equals to minus k Boltzmann T of log phi over k and s, of what? Of zks. Now our zks equals to 1 plus e to the power minus beta h bar squared k squared divided by 2m. Here I have minus mu. This is the grand canonical potential. Now look on this. What is the summation over, or I'm sorry, multiplication over s? Is just taking to the second power each term with a specific k. Because for each k, I have two particles. I have a degeneracy of two. One is spin up and one with spin down. So since a logarithm of multiplication is the sum of logarithms, and here I would have a second power after multiplying everything over different s's, what I will have in total, that psi equals to minus k Boltzmann T, a summation over different k's, factor 2 over here because of the degeneracy. Here I will have 1 plus e to the power minus beta h bar squared k squared divided by 2m minus mu. I close my parenthesis. Okay, so this is the grand canonical potential. This is a nasty sum though, right? So have to sum over all different k's. What are the different k's? I don't really know. But we already have seen a way to actually take an upper hand of this problem. Instead of summing over all different k's, you remember we replaced the summation by an integration. Okay? And when this integration was performed, when we not just integrated this, but we took the Jacobian of the density of the different k's. So psi would be equal minus 2 k Boltzmann T, an integral, k goes from 0 to infinity, of 1 plus e to the power minus beta h bar squared k squared divided by 2m minus mu d prime omega d omega. You remember what is d prime omega is the volume divided by 2 pi squared. 2 pi squared k squared dk d omega. Now we are much more interested in the representation of epsilon equals h bar omega. So we have d of epsilon equals to v divided by 2 pi squared k squared dk d epsilon okay, multiplied by h bar. Multiplied by h bar. So the epsilon equals this guy multiplied by d h bar omega. I'm sorry, d epsilon divided by h bar. And what we obtain over here, that is equals to v divided by 2 pi squared k squared dk d epsilon. So great. This is one small step. By the way, what is the connection between k and epsilon? Because we still have here this term of k squared. Okay? So the connection is that epsilon equals h bar squared k squared divided by 2m. Okay, so k equals to what? K equals to 2m divided by h bar squared multiplied by epsilon. So dk d epsilon equals to square root of 2m divided by h bar squared multiplied by 1/2 square root of epsilon. Okay. We can plug in all of this k and dk d epsilon into this formula over here in order to obtain the grand canonical potential. What is the grand canonical potential? Again, we have this integral between 0 and infinity. So psi equals to what? Minus 2 k Boltzmann t. Okay. An integral between 0 and infinity. This form over here, which is 1 plus e to the minus beta. Instead of h bar squared, k squared divided by 2m, it's just epsilon minus mu. Oh, I'm sorry, I forgot log over here. Here was a log. Here it also should be a log. So it's a log of 1 plus e to the minus beta epsilon minus mu. Then I should multiply everything, but what is stands over here? So it is v divided by 2 pi squared. V is the volume of the metal that I'm trying to measure. K squared. What is K? K is 2m divided by h bar squared epsilon multiplied by dk d epsilon. What is dk d epsilon? It is square root of 2m divided by h bar squared multiplied by 1 of square root 2 epsilon d epsilon. Okay. This is our grand canonical potential. So what we have left with is, let's take everything that we can out, which means minus 2 k Boltzmann t. We have v. Here we have 2m h bar omega, 2m h bar squared. So we neglect this, divided by pi squared. We have 2m divided by h bar squared, 3/2. We should have also a square root of 2 over here, and we are left with an integral between 0 and infinity of epsilon 1/2 log of 1 plus e to the minus beta epsilon minus mu. All of this, of course, d epsilon. This is the grand canonical potential of the Fermi fluid. Not a very nice function, right? Now, if we want to compute something like the average number of particles inside the system, it becomes even more uglier, right? Because what is n? According to the definition of the grand canonical potential, it's simply minus d psi divided by d mu. So we should take this integral, this expression, and take the derivative with respect to mu over here. Actually, you do not need to remember those formulas. And usually you don't really need to perform those derivatives over here, right? Because much more nicer expression is going to be, well, what is n average? N average is the sum of what? Of over all case, okay? And for all this case, there is either the state with k is occupied, then if it's occupied, I have exactly one particle over there, or the state is not occupied, so I have 0 particles over there. In any case, the 0 particles doesn't contribute anything, because it's 0 multiplied by the probability of this state not to be occupied. I don't care about anything that is multiplied by 0. It's strictly 0 for me. So here I just have to sum up over all different states, and basically over the probabilities of those states to be occupied, right? Because there is only one particle per state. Now, what is the probability of a specific state to be occupied? It's simply 1 over, it's just the Fermi function, right? So it's simply 1 over e to the power beta of what? Of epsilon k minus mu. Okay. Now, all of these guys I have to multiply by 2. Why? Because, well, there is degeneracy of 2 per state. Okay? Because it can be with spin up and spin down. Okay, so when we take this guy over here, sorry, and plug everything in, so we can stay, well, we should do exactly what we have done for this grand canonical ensemble. Okay. Exactly the same stuff. Okay, so I should write down that average n equals to 2 multiplied by an integral between 0 and infinity of 1 divided by 1 plus e to the power of beta of epsilon minus mu d of epsilon d epsilon. That's it. I already know what this d of epsilon is because I have calculated this guy before. Okay. So what I have left with is again that n average is simply v divided by square root of 2 pi squared. Okay, square 2m divided by h bar squared to the power of 3 halves. And here I have an integral between 0 and infinity, epsilon to 1/2, e, here 1 plus e to the power of beta epsilon minus mu d epsilon. That's it. Now, if I want to compute the average energy, U, average energy, what's going to happen? It's again the same prefactor over here, the same prefactor over here, and I will have V divided by square root of 2 pi squared 2m divided by h bar 3/2 integral between 0 and infinity epsilon multiplied by epsilon to 1/2 divided by 1 plus e to the power beta epsilon minus mu d epsilon. So always the same thing. It's coming from what is n average is 2 and the sum over all different possibilities. What is the average energy? The energy of the state. If it's occupied, it's epsilon. If it's not occupied, it's 0. Okay? And I have to sum over all different states. That's it. So I will always come to this integrals between 0 to infinity of the Fermi energy multiplied epsilon to the power 1/2 because it came from the density of states. And here I will plug in whatever I want to average over. Its energy is going to be either over here. Its number of particles per state, it's just 1. I want to average the square energy, it's going to be e to the power 2 over here. Very, 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 very simple. Right? The moment we have the Fermi energy, the moment that we have the behavior for pair 1 particle, that's it. You know what the energy of Fermi, if you know the mu, and you sum up over all different states, and every time this summation over states is just becoming this integral between 0 and infinity, Fermi energy, epsilon to 1/2 density of states, and the thing that you want to average over. Very, very simple. This is why the Fermi function is also called the Fermi distribution. It's like a distribution over here. Okay. So this was a nice exercise, right? We had particles, we have states, we call that they had no interactions, we obtained final results. This is some integral over here, but we don't really care because we know how to solve all the integrals in the world. Now, is this real? Okay. So what can I say about how, if I'm going to apply this particular model for a real system, how can I know, or why should it all describe some electrons inside a metal? I already told you that there are screening fields and that these energies, interaction energies, are completely unimportant. Well, if they are unimportant, what should I see? I should see that the energies of the particles that are sitting near the Fermi energy are very, 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 very high. Why is this important? Because if the Fermi energy is low, okay, the Fermi energy is low, even in low temperatures, if the Fermi energy is low, then all the particles that are interacting and actually participating in the game, they are going to be affected, their own energy and their energetic levels are going to be affected by the interactions with nearby particles, even if there are screening fields. I don't care. If my energy is low and the interaction energy with other guys is on the same level, well, I cannot neglect it. When I can actually neglect the interaction energy, only with when my kinetic energy, my own energy, is very, very, very high. So what I expect that this model should work only in the cases when the Fermi energy is very, very, very high, or the effective temperature of those particles that are sitting near Fermi energy are very, very high. Then I can say, well, this is actually a gas. There are some interactions, but I don't care because the kinetic energy is extreme, is enormous, is very, very high. Okay? So what we going to do next, we're going to say, well, we know what the average energy, we know what the average number of particles. Because I have a metal, I know what is the density of the molecules inside, what is the electronic density inside. I know what n is. Now, from n, I know, we've already seen it, I know how to compute the chemical potential. Chemical potential is my Fermi energy. So let's take a known n for a room temperature or whatever, for any temperature, low temperature, and approximate or calculate the Fermi energy of the system. If the Fermi energy of this system is low, well, I would say this model doesn't worth anything. Because, well, it neglected interactions, but the self-energy, the kinetic energy is low, so interactions are going to affect everything. But if the Fermi energy from this calculation is going to be very high, I can say, well, it should work. This model should work. Why? Because the interaction energy is small, very small compared to the self-energy as it obtained from this model. So let's see what the Fermi energy for a real system, when we know what is n, and more importantly, when we know what is V divided by n. Okay, because this is the density. This is simply the density, right? I'm sorry. Yeah, this is the density of the electrons inside the metal. This I can calculate. This I could know what's actually going on inside the metal. Right? So we will take a real system with real values of V divided by n, and we calculate mu Fermi, okay, in the limit of low temperatures. Why it's important the limit of low temperatures? Well, because in the limit of the low temperatures, I know how the Fermi function behaves. It's simply a step function, okay? Because I know that in the limit of t goes to 0, 1 plus e to the power beta epsilon minus mu goes to, t goes to 0, it goes to what? It is 1 for epsilon lower than mu, and it is 0 from epsilon higher than mu. I have this step function. So it's very easy to compute this integral. It's very easy to compute this integral in the limit of low temperatures. Okay? What we see that if t goes to 0, n equals to v divided by 2 pi squared 2m divided by h bar squared to the power of 3/2. That's an integral of epsilon to 1/2 divided by 1 plus, divided by what? So here I should have, let's write it down, 1 plus e to the power beta epsilon minus mu d epsilon, and it goes from 0 to infinity. But in the limit of the low temperatures, this guy, 1 over 1 plus e to the power beta e minus mu, it's 1 up to what? Up to mu Fermi, and it's 0 afterwards. Okay? So we can rewrite this integral over here as a simple one, without all of those exponentials. Right. What we have n average equals v divided by square root of 2 pi squared 2m divided by h bar squared 3/2, and here we have an integral between 0 and mu Fermi of epsilon to the power 1/2 d epsilon. Right? Nothing more, nothing less. What we obtain is that n equals v divided by square root of 2 pi squared 2m divided by h bar squared 3/2 multiplied by 2/3 of mu Fermi to the power of 3/2. Okay. So, and what is mu Fermi equals to? So it equals to 2. Right. So it equals to n divided by v multiplied by pi squared multiplied by 3 divided by square root of 2. And here I have h bar squared divided by 2m 3/2. All of this to the power of 2/3. This is my mu Fermi at low temperatures. Now, if we take the density to be in real metal density, so n average divided by v on the order of 10 to 22, 10 to 23. This is what happens in real metals, right? What we get that mu Fermi is on the order of mu Fermi divided by K Boltzmann. It's on the order of 10 to the 4 till 10 to the 5. So mu Fermi is 10 to the 4, 10,000 K Boltzmann T. 10,000 or even on 100,000. So all the particles, so if we plot F, and this is epsilon divided by mu, so this is what happens to the particles. And here are the particles that are participating in the process in the low temperatures. Those are the particles that are actually doing something. Those are the states that are contributing particles, getting particles, etc., etc. The energies of those states is as though the particles there are in the temperature of 10,000 Kelvin or 100,000 Kelvin. Huge numbers. Those are free particles. This is it's a gas and it's a very high temperature. Let's consider that there is a particle and its kinetic energy, which is mu Fermi, is 10,000 Kelvin. Okay? The interaction energy is on the order of 3 K Boltzmann T, 4 K Boltzmann T, 5 K Boltzmann T. I will completely forget everything. 100 K Boltzmann T. This is the interaction. Okay? It's not going to affect its energy whatsoever. Okay? The main part, the strongest part here is coming only due to that the particles are free, and this is because there was a lot of particles and there was a lot of states to fill up. So the statistics pushed all the particles very high up. The energy, the Fermi energy is pretty high. It's pretty high. So the energies of all those particles, of all those electrons, is very, very high above. Now, if I'm adding or subtracting from this some interaction, it's not affecting the particles, or almost does not affecting the particles. So I can actually assume that the particles are free. This is what I've seen from my calculation. Even if in the limit of very low temperatures, I see that the contribution of the energies, kinetic energies are extremely high. So adding or subtracting another interaction and making something else for this gas is not to qualitatively change anything. Okay. So this is why the Fermi fluid model is actually describing very well for a lot of motors its behavior, even in low temperatures. This is actually important. Okay, so we covered up the fermions. What we have still left with are to say some words about the boson space. Now, it's very, very similar. So you have a statistics, but this time the statistics of bosons does not have any complications, meaning per state there can be 0 particles, 1 particle, 2 particles. Okay? There are no restrictions. So if I'm again trying to plot everything, let's go to the Bozek fluid. Okay? And I'm having my energetic spectrum E. There are different energies. Beforehand, I could have 1 particle per state, or if they had different spins, okay, so spin up, could have spin down. Now time, because it's bosons, I don't have Pauli exclusion principle, so I could have 1 particle spin up, 2 particles spin down, 3 particles spin down, so I don't care. Or 2 particles with spin up, 1 particle with spin down. Okay. I completely don't care about the number of particles that are sitting per each state. The only thing that I should care is, well, the total number of particles in a closed system is constant. But I've already solved this. How I solved this? I said, well, let's treat everything in what? In a grand canonical ensemble. And if I'm treating everything in a grand canonical ensemble, well, I shouldn't care about this restriction of constant number of particles. I'm just summing over all possible situations, right? So how should I calculate the partition function of a Bozek system? Okay. And you have Z, and it should have a sum over all possible k's. What is k over here? K prime, let's say. E to the power minus beta epsilon k prime minus mu n k prime. This is the general partition function. I take a specific state, I note that it's a k prime, and in k prime it has an energy of epsilon k prime, okay, minus mu multiplied by the number of particles for this k prime state. Now, but what is the energy? The energy is just the number of particles at all the different states. Okay? So I'm going now by proving K1, K2, K3, K4. Okay? What is K1, K2, K2, K3, K4? The number of particles at state epsilon 1. K2 is the number of particles at state epsilon 2, and K3 is the number of particles at state 3, and etc., etc., etc. Here what I have, it is exponent of minus beta, and I have K1 epsilon 1 plus K2 epsilon 2 plus K3 epsilon 3 plus etc., etc., etc. Okay, so this is the energy of the system. Just sum up over all different energies. No interactions between the particles. Minus mu, and what I have here, well, the total number of particles at this specific state, which is the number of particles at epsilon 1, the number of particles at epsilon 2, the number of particles at epsilon 3. So it's K1 plus K2 plus K3 plus etc. 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 So the same idea as for the fermionic case. Now what we are doing, we're splitting up, we're factorizing everything. So Z is a sum of where K1 e to the power minus beta K1 epsilon 1 minus mu K1 is multiplied by the sum of K2 of exponent minus beta K2 epsilon 2 minus mu K2. The sum up of K3, etc., etc., etc. Now, so it's a multiplications we are doing. Z now, it's a multiplication over different K's and different S's, different spins of ZKS. What is ZKS? It's simply a sum over I over I e to the power minus beta I epsilon k minus mu I. Okay. I goes from 0 to, for the fermionic case, is just 1. For the boson case, well, could be an infinite number of particles. Can I have a system that have infinite number of particles at state 1 and infinite number of particles at state 2? Yes, of course. This is the point of grand canonical potential. I don't care about the restriction of the number of particles. Okay, what is the sum? Zk of S. What is the sum? It's just 1 over 1 minus e to the power minus beta, right? Minus beta over epsilon k minus mu. Okay, it's a geometric summation. Now, it's very, very much similar to what we had for what? What we had for the fermions. The fermions, there was the other way around. Now, I can ask myself now, what is the probability of state K to be occupied? Okay. Now, beforehand, I had to ask, well, occupied and unoccupied is very two distinctive states. Here, when I'm saying occupied by how many particles, right? So I can ask the probability F of the state K and S to be occupied by n number of particles is simply what? Is simply e to the power minus beta n epsilon k minus mu n divided by zeta ks. Okay. I'm sorry. This is very simple. And if I want to compute the average number of particles, what should I do? Well, the average number of particles at state K, S, is simply n goes from 0 to infinity, psi K, S of n multiplied by n. what we can obtain, first of all, it's never dependent on n(s). N of k is simply what? N of k is going to be 1 over e to the power beta epsilon k minus mu minus 1. Remember, the number of particles, or the average number of particles per state in the fermionic case was 1 over e to the power beta epsilon k minus u plus 1. And in the bosonic case, the only thing that changes is this minus 1 over here. That's all. I would say, well, the results are very close by, nearby. Those systems are not really much different from one each other, but it's actually very far from the truth. The truth is that when the energy of the state exactly equals to the chemical potential, basically the Bose energy to mu, the average number of particles diverges. What it means? So, well, I'm actually going to have an infinite number of particles at this specific state. What does this infinite number of particles actually means? What it means is that there are specific situations for the Bose system when the macroscopic of almost all the system, there is no infinite number of particles, but all the system, or the macroscopic part of the whole system, is going to occupy one single state. It's called a Bozek condensation, and it's actually a mathematical result because we have minus 1 over here. I'm not going into the details because there are some lengthy and cumbersome integrals involved, but it is clear that there are situations when something starts to diverge, the signature of some phase changes that happens to the system, and this Bose condensation is actually something that we can study and observe experimentally. There are superfluidity, so at low enough temperatures, everything, the fluid can become superfluid, which means that it just flows from one place to another without any friction. Okay? Without completely any friction. What happens there? Well, all the system sits in a very low state, and the state above, okay, the next state, is actually well separated, quantumly well separated. So what is friction? Friction is when you lose energy to the system. So you have a fluctuation, okay, you increase your own energy, and then you lose some of your energy to the environment. This is friction. Okay? Friction is actually when you're having some energy and you're losing your energy to the environment. But when you're sitting in a very low state and you don't have any options to lose because there are no particles in an unoccupied state. Everything is sitting below some, here it's called a Bose energy. You don't have fluctuations that actually affects you and causing you to lose some sort of an energy. So there is no friction. Exactly the same happens for superconductivity. Okay? There are two labs here in Bar Ilan, one of Professor Shirun and another one of Dina Kaliski. And they study the superconductive properties of the materials. What happens there? Well, you can say those are fermions, those are electrons. There are no Bose condensation there, but actually the interactions that we neglected, okay, the interactions with the media that we neglected, for some materials, they are very, very strong. And the Fermi fluid description does not hold anymore. And what you have, that this exact interaction couples different electrons, and when they are coupled to each other, they effectively create a Cooper pair. A Cooper pair is a particle which have spin not 1/2 but 1. So it became, instead of being a fermion, a single electron, it became a boson. And bosons can have Bose condensation. And this is exactly what happens over there. So you can have conductance or superconductance. You have no resistance in the material, although it has very much of resistance in the room temperatures. For low enough temperatures, We're not having anything because, again, of this feature of Bozek condensation. All the system just sitting in a very, very low energy, and it cannot contribute any energies to fluctuation. What is the resistance? Resistance and friction is exactly the same thing. Right? You're not losing energy because it's impossible for you to lose anything. Again, it kind of happens from this small minus over here. I will stop here, and the next two lectures, which are the final lectures of this class, we are going to see systems where the interaction is actually important. So up till now, we studied a lot of the system and a lot of the ways how to treat non-interacting particles. So we know everything how to solve about non-interacting systems, but most of the systems are have interactions. So what we are going to do with interactions, some of this material we are going to cover in the next two lectures. Thank you.